Because of the stirring? All right. Just a reminder, make sure you schedule a time with me about the oral final and when you're going to plan on taking the other portion of the final. I'll get a review sheet done for the other portion of the final probably today and get it posted on Moodle so you have that. Hello.
Hello.
So again, remember I'll call it in-class portion of your final is just over the group stuff that we've done since the last test. All right, so let's take a look at this problem that I handed out that I was too lazy to reprint, so I just snipped it and copy printed it instead. All right, so we've talked about finding the number of elements of a certain order in a cyclic group, and we've talked about how isomorphisms, if two groups are isomorphic, then they have to preserve absolutely everything about the structure. So one of the things that we're going to use to show that two things aren't isomorphic in particular is that they would have different elements of a certain order. But we can use other structure pieces as well. So notice the first part in part A in that problem that I gave you said y is Z36 not isomorphic to Z12 cross Z3, and it's also not isomorphic to Z6 cross Z6. Well, what do you know? What kind of group is Z36? Any of the Z mod n groups are what? Apparently they're quiet. They're cyclic. Good. All right. So any of the Z mod n groups are cyclic, right? So Z36 is cyclic. In order for a direct product to be cyclic, you need each piece to be cyclic. And what else do you need to have true about their orders? Talk about that. What?
The part that was divisible.
Yeah, part of that. Yeah. Has something to do with the divisibility idea. For example, with the Z12 and the Z3, what are the orders of Z12 and Z3? 12 and 3. What do you notice about those numbers?
They're not relatively prime.
Yeah, they're not relatively prime, right? That's the big deal. So in order for the direct product to be cyclic, you need both groups to be cyclic and their orders to be relatively prime. So if Z mod M cross Z mod N is going to be cyclic, then you need M and N to be relatively prime. So Z36 is cyclic. Is Z12 cross Z3 cyclic? No. Is Z6 cross Z6 cyclic? No. So why is Z36 not isomorphic to those other two groups? They're not all cyclic, right? Good. Because remember, they have to have exactly the same structure if they're going to be isomorphic. So so for your answer for part A, Z36 is cyclic, but Z12 cross Z3 and Z6 cross Z6 are not. I don't have it explicitly asked for here, but tell me why you know that Z36, Z12 cross Z3, and Z6 cross Z6 are not isomorphic. None of those three are isomorphic to D18, and none of those three are isomorphic to D6 cross Z3. What's different about the Z mod N or the direct product of Z mod M and N versus the dihedral groups? What does one thing have a property? What property does one have that the other doesn't? And don't think hard about it. I mean, it should be a basic property. Why did we start with one of the dihedral groups to introduce rings? What was true about the operation? Same idea as matrix multiplication. What's true about that operation? Not commutative. So what can you say about Z36, Z12 cross Z3, and Z6 cross Z6? What property do all three of those have that the other two don't? Say again.
They're commutative, but the G18 and D6 are
Good, exactly right. So Z3, the ZN, the Z36, the Z12 cross Z3, the Z6 cross Z6, those are all abelian groups. The D18 is not abelian. The D6 is not abelian, so the direct product can't be abelian, right? So notice in our list here we've got two non-abelian groups and three abelian groups. Oops. They cannot be isomorphic if one has a commutative operation and the other one doesn't. Okay. So when I'm asking you questions like this, and you'll see another one of these on the review that I hand out to you or post on Moodle later today. When I ask you a question like this is those basic kind of properties I'm asking you about. One's cyclic, the other's not. One's abelian, the other's not. Okay. They can't be isomorphic if they don't have those same structure ideas. So basically right now we've got Z36 in a class by itself, right? It's certainly not isomorphic to any of the other ones. The two other abelian ones are not cyclic, and the other two are not abelian, so it's all by itself. Okay. So it's definitely a distinct group from the other four. So let's say the next two questions are asking us to show that these two groups really are distinct from each other. Okay? All I have right now is neither of them are cyclic and they're both abelian. Well, if they were going to be isomorphic, that's good, right? They're both not cyclic, they're both abelian. Those are similar structures to each other, right? And they have the same size, by the way. That's probably basic idea number one. They have different sizes and they can't be isomorphic to each other. But they both have order 36 here. So the next one's asking us to, pardon me, count out the number of elements of each possible order in both of those groups. All right, so let's do it in pieces. So let's look at the Z12. What are your possible orders of elements? We talked about this before. I'm purposely doing this as partly like a review, too. What are your possible orders of elements here? Okay, so it's more restrictive than that, right? Because what has to be true about the order of an element relative to the size of the group? No, I heard one correcting it. They're all the ones that I just heard. Which one was it? It divides it. Yeah, remember the order of the element has to divide the order of the group. So these are your possibilities. Now the relatively prime piece will pop up here in a second, especially for these elements, order 12. But those are your possible elements of order 12, or of the possible all the possible orders of elements in Z12. How about for Z3? Yeah, it's just 1 and 3, right? Good. All right. We okay with that? The possible orders are the divisors of the order of the group. We talked about it for cyclic groups by the time we're done on Thursday, we'll have it true for any group. That the order of an element has to divide the order of a group. Okay? All right. Now, how did you count the number of elements of each order? What function did we use to count the number of elements of each order of a group for a cyclic group? In particular, for example, how do you figure out the ones that have order 12? What has to be true? I think you said that earlier.
Prime themselves, like they have to act themselves 12 times to operate. Operate on themselves 12 times to get to the identity.
Okay, so that's exactly what it means to have order 12. That if you operate it with itself 12 times, you get back to the identity, and no smaller thing works. But what was true about the element in Z12 and the order 12? What do you need true about the element in Z12 that has to have order 12?
That is the order of the group.
Multiplies by 12 because
Okay, looking for a. Okay, so 1 certainly works, right? Give me another element that has order 12. Try it this way. Well, 12 is the same thing as 0. So 0 only has order 1. What else has order 12?
Is that 11?
11 is, yep, good. What else does? There's 2 other ones.
Oh, it's the ones that are relative.
The ones that are relatively prime. You said relatively prime earlier, right? Yeah, so the elements that are relatively prime will give you order 12. So the number of elements in Z, this is for Z12. Oops. That was weird. For Z12, your number of elements of order 12 is 4 in this case. And again, what function tells you that? There's a special function that we've talked about this semester that tells you things.
It's like a fee.
Yeah, it's the Euler phi function. Good, yeah, so it's phi of 12. And in particular, in a cyclic group, for every divisor of the order of the group, there's phi of that number elements of order, whatever it happens to be. So if you want elements of order 6, then that would be phi of 6. And what is phi of 6? How many numbers are less than 6 and relatively prime to 6? How many integers, I guess I should say.
1.
And 5. So how many of them total? 2. There we go. Good. Do the same thing for 4 and for 3 and for 2 and for 1. Of course, how many elements of order 1 are there in any group? No matter what. 1. Good. Elements of order 4. It'll be 2, right? 1 and 3 work. Elements of order 3. 2. Elements of order 2. 1. Good. And you can now, what should if I add all of these together, what should I get? 12, all right? Do I get 12 when I add all those together? Okay. Do the exact same thing for Z3. How many elements of order 3 are there for Z3? Two, good. And order 1, good. No matter what the group is, how many elements of order 1 are there? Just 1, good. All right. Remember, this Euler phi function part works because of the fact that we have a cyclic group. If the group is not cyclic, then it has to be a multiple of phi of the divisor. All right. You okay with counting number of elements of a certain order? Okay. Notice the problem asks you, part B asks you in that sheet that I handed out, the number of how many elements of each possible order there are there in the direct product. Remember, when you're in a direct product, actually this is not, I can do this in any cycle or any direct product, but if I want to do the order of a element in a direct product, and again, it doesn't have to be Zm cross Zn, but that's what we're talking about right now. If I want to do the element of an order, sorry, try that, I said it backwards. Order of an element in a direct product, what do I look at? How do I find the order of an element in a direct product? Yeah, least common multiple of the orders, right? So this will be the least common multiple of the order of A and the order of B. Good. All right, so now so we're trying to do Z12 cross Z3. What are our possible pairings? Well, I can take an element of order 1, 2, 3, 4, 6, and 12 and pair it with an element of order 1 or 3, right? We agree? I can take an element of 1, 2, 3, 4, 6, 12 in Z12, take an element of order 1 or 3 in Z3, and pair them, right? So what are our possibilities? You got 1 and 1, 2 and 1, 3 and 1, 4 and 1, 6 and 1, 12 and 1, and then do the exact same thing with 3. 1 and 3, 2 and 3. I should have written this smaller. 4 and 3, 6 and 3, 12 and 3. Oh, I'm missing 3 and 3. Thank you. Oh, I figured that out when we totaled it up and got the wrong number of elements when we were done. Okay. So let's think about now what happens when you pair these up. If I take an element of order 1 and pair it with an element of order 1, what order do you end up with? 1. Element of order 2 paired with element of order 1, 2. 3 and 1 make 3, 4 and 1 make 4, 6, 12, right? Those are all pretty straightforward, right? Okay. Let's do the other way. 1 and 3 paired together give you 3. 2 and 3 paired together give you what? 6, because it's the least common multiple again, right? 3 and 3 paired together will give you 3. 4 and 3 give you 12. 6 and 3 give you 6. And 12 and 3 give you 12. Everybody see where those are coming from? This is good in the least common multiple of those two things. Right? We're pairing elements of a certain order in Z12 with an element of a certain order of Z3 and looking at their least common multiples. I'm just writing out the list of possibilities. Finally here, in my last column, let's count how many there are. How many elements are there in order of order 1 in Z12? 1, and then how many elements are there of order 1 in Z3? 1. So I have to take the element of order 1 in Z12 with the element of order 1 in Z3 and put them together. So how many possible ways can I do that? 1. Good. Let's do a little bit more interesting example, and then we'll fill out the rest of the list. Let's say I wanted to do this one right here. I pair an element of order 4 with an element of order 3. In Z12, how many elements of order 4 are there? 2. In Z3, how many elements of order 3 are there? Also 2, right? So I could have 2 choices for my element of order 4 and 2 choices for my element of order 3, and I put them together. How many total ways can you do that? 4, yeah. So you'll do, notice this is just a counting problem, right? I say just a counting problem. I don't mean that, because counting is hard. Combinatorics is hard stuff. Make that joke of counting being hard. No, counting is freaking difficult. What a question. Speaking of that, has anybody seen the clip of the little kid eliminating 5 and 6 from counting from 5 to 10? If you're not offended by little kids saying what sounds like a bad word, it's hilarious. Combines the 5 and 6. The mom's trying to go 5, 6, 7, 8, 9. No, and then yeah, sounds like screw 7, 8, 9, 10 is what it sounds like. It's hilarious. Anyway. All right, so how do we do the rest of these then? These ones at the top are not all that interesting. How many elements of order 2? We had 1 element of order 2, 1 element of order 1. So again, there's going to be 1 element here to do that. There's 2 elements of order 3, 1 element of order 1. So you'll get 2 times 1, or 2 elements of order 3. You'll get 2 elements of order 4. You'll get 2 elements of order 6. You'll get 4 elements of order 12. We already counted those other ones, didn't we? Do you see where we're getting these do you see where I'm getting the factors from? That I'm multiplying together.
Not really.
Okay. I kind of figured what the looks I was getting. Okay. I'm looking at these 2 lists that we came up with before. When I'm making up the element in the direct product, I got to take something from the first group and something from the second group and piece them together. We know when we put them together, the order of the ordered pair is the least common multiple of the orders of the 2. Right? Are we okay with that part? Let me go back to this. Are we okay with where I'm getting this list from? This list of numbers here is just the least common multiple of these 2 going across. That part okay? Okay. The reason why I listed it out this way is because if I look at a particular row, I'm just figuring out the different ways that I can piece things together to give me an ordered pair. One of the one I just circled up there, I can take an element of order 4, pair it with an element of order 1, that gives me an element of order 4, because that's the least common multiple of 4 and 1. Right? How many elements of order 4 are there in Z12? Well, there's 2, right? Yeah, okay. There's 2 elements of order 4 in Z12. There's 1 element of order 1 in any group, but in Z3 in particular. So that's where this computation is coming from. Because I'm just counting number of ways to choose the first component number of ways to choose the second component and then multiplying them together. So what if we do, gosh darn it, stop it. What if we do, no, none of these are all that interesting because they're small numbers. If I look at this one here, there's one element of order 1, and there are, in Z12, there's 2 elements of order 3 in Z3. So we get 2 total. The next one is also 1 times 2, because there's 1 element of order 2 and 2 elements of order 3. 3 and 3, I would use 2 times 2. Because there's 2 elements of order 3 in Z12, 2 elements of order 3 in Z3. We would also use 2 times 2 for a 6 and 3. And then the last one we would use 4 times 2 and get 8. When I add all those numbers up in that list, what should I get? How many total should we get when we're done? 36. Good. Yeah, there should be 36 total, right? 2, 4, 6, 8, 12, 14, 16, 24, 20, 24, 28, 36. It doesn't add up to the whole to the group, and then we've made a computation error somewhere along the way. All right. So now let's total everything. Notice your only possible orders are 1, 2, 3, 4, 6, 12. That's it, right? The only possibilities we got. So now let's total everything up. How many elements of order 1? 1, good. How many elements of total elements of order 2 are there? 1, good. How about 3? That one actually is going to be different than 1. I see 8. Yeah, good. There's 2 here, 2 here, 4 here. So there's 8 total. Order 4. Two, order 6. And there's 8 total, isn't there? There's 2 here, 2 here, and 4 here. And then 12. How many did you say? Too many? 16, good. Again, that total that we just came up with, if I add all those numbers up together, how many should you get? 36, and we do. Phew. We only have to do this 3 more times. All right. Let's do the same thing now for Z6 cross Z6. That one should be a little shorter. I will still write it in 2 columns, though, just to kind of keep things a little bit more organized. What are your possible orders of elements in Z6? Good. 1, 2, 3, 6. And I got to pair it with any of the other elements. So I actually have to do this. This gets a little long, but that's okay. Now let's do it this way. Let's think about least common multiples first. If I take an element in Z6 and pair it with an element in Z6, what are your possible least common multiples of orders now? It's the same, right? It's the same exact list, isn't it? Okay. So these are your, what would be 12?
I missed how many elements? 12.
Oh, 16, sorry. You're welcome. All right, so now if we do Z6 cross Z6, we have elements of order 1, 2, 3, 6. Again, we ask how many. Let's see if we can do it all at once rather than having to list them out row by row like we did before. How do you get an element? What has to pair together to give you an element of order 1? Yeah. To get an element of order 1, I have to take the element of order 1 with the element of order 1, right? How many total elements are there of order 1? Just the 1, right? Always. How can you get a least common multiple of 2? What can pair together to give you a least common multiple of 2? Think about the orders first, and then we'll do how many. How can you pair orders together to give you a least common multiple of 2? What can pair together? One and two, 2 and 2, 2 and 1, right? You can do 1 in the first one, 2 in the second one, 2 in the first one, 2 in the second one, 2 in the first one, 1 in the second one, right? So I got 3 separate cases. I just didn't write them out. If I would have wrote it out in rows, I would have had to write, what, 16 rows down? Okay, I had to pair each of the ones with the 1, each of the ones with the 2, and so on down the line. All right, so you said 1 and 2. I'm just going to write it above so that we can see what they are. 2 and 2, 2 and 1. Let's see what we need to add together. How many elements of order 2? Remember, in a cyclic group, order of order D is phi of D, right? Doesn't matter what the order. It doesn't matter what the divisor is. The number of elements of that order is the Euler phi function of that order. So number of elements of order 2 is 1. Or number of elements of order 1 is 1, right? So there's only 1 total here, 1 total here, 1 total here, right? Because there's only 1 element of order 1 and 1 element of order 2. So if I pair those together, that's only one way to do it. There's 1 element of order 2, 1 element of order 2. Pair those together, there's only one way to do it. 2 and 1, there's only one way to do it. I'm just doing 1 times 1 in that case. These are distinct cases, so to get to the total, what do you think we want to do with those 3 numbers? I want the total number of elements of order 2. Add them, yeah, good. So there's 3 total elements of order 2. Again, working with least common multiples, what has to get paired together to make an element of order 3? Or what can be paired together to get an element of order 3? Yep, 3 and 1, 1 and 3, 3 and 3, right? How many elements of order 3? No matter the cyclic group, how many elements of order 3? 2, right? So 3 and 1 together will give you 2 total. 1 and 3 together will give you 2 total. 3 and 3 together will give you 2 total. So we get 6 total. That means how many should we get when we find the elements of order 6? How many better we count? How many have we counted so far? 10. So how many more should we find? How many more we better find? Well, the Z6 cross Z6 has what size? 36. So how many more elements should we find? 26, right? There better be 26 total when we're done. Okay? So we need a least common multiple of 6. We can use 6 with anything, right? That'll give me 6, right? And then anything with 6. And then the 2 and the 3 and the 3 and the 2. Okay? We got lots of cases for this one, don't we? You can do, make sure I am gonna write these down, make sure we get them all. Okay? You can do 6 and 1, 6 and 2, 6 and 3, 6 and 6, 1 and 6, 2 and 6, 3 and 6. I don't want to do 6 and 6 again. I've already counted it. I'll double count if I do 6 and 6 again, right? The other two are 2 and 3, 3 and 2. Agreed? Those are the possibility. 6 and anything and 6, 2 and 3, 3 and 2. That's what's going to give you at least a multiple of 6. Yeah. Okay. And then we use our Euler phi functions again and multiply. How many elements of order 6 are possible? 2. Good. So this will be 2 times 1. This will be 2 times 1. This will be 2 times 2. This will also be 2 times 2, right? So those will all be 2, 2, 4, 4. And the same idea here, 2, 2, 4 for those. And then finally, the last one should be 2 and 2. Phi of 2 is 1 and phi of 3 is 2. Multiply those together, we get 2. Did we get 26? I hope. 2, 4, 8, 12, 14, 16, 12. What did I miss? 12, 16, 20. I had 24. Somewhere along the way, we got the wrong number. 1, 2, 3. 16 pairings. Oh, I know where it is. It's not down here. Jeez. I can't multiply. Sorry. I calculated that one wrong when I did the 3 and the 3. That's 2 times 2, isn't it? Phi of 3 is 2. If I put a 3 and 3 together, there's 4 ways to do it. Oh well, anyway. Whew. There's 26 or 24 total here. Now we got 36. All right. The whole point of this now was to show that these two groups are not isomorphic. In particular, zooming out too far. Z12 cross Z12 cross Z3 has an element of order 12, doesn't it? Does Z6 cross Z6 have an element of order 12? No. So can they be isomorphic? No. I really thought you might enjoy the counting problems more today, but clearly I was not right. But I'm glad I'm going over it because these are important concepts to remember. All right. D18. Remember your dihedral groups? Half of your elements are what type of things? And the other half are reflections, right? How many reflections are there? Say that again? It depends on the group, right? Depends on the dihedral group, how many you have, right? So if we have a triangle, for example, we got 1, 2, 3 reflections, right? We did the square. How many reflections did we have? Reflections. Four, right? So in general, if you have dihedral group, half are rotations, half are reflections. So how many reflections is this one going to have? Remember, half are rotations, half are reflections. So how many elements does D3 have? Total elements, 6. How many elements does D4 have? 8, but half are reflections, half are rotations. So up here again, there's 18 reflections and 18 rotations. Yeah. Yep. How many? No matter what reflection you have, what's its order? How do you undo a reflection? Just do it again, right? So what's the order of any reflection? 2. Good. All right. So every Dn group will have at least n elements of order 2. Depending on the n, there might be one more element of order 2. So let's ignore the reflections for the time being and go back to the rotations. What type of group does the rotations form? What special type of group does the rotations form? It's a cyclic group. It can be generated by that. I like to think of it as clicking. You take one vertex and you click it one time. That's one click, right? Just do the one click rotation. That generates everything, right? Because I can generate all the clicks by doing one click at a time, right? So the rotations, why does it keep opening Google? The rotations form a cyclic group of order 18. Oops. So now you should be able to count the number of elements of each order in that group. Because a cyclic group of order 18 may as well be Z18. How do we count number of elements of certain orders in a cyclic group? What do we look at? The FE function and look at the divisors, right? Right? So what are your possible divisors then? What are your possible orders? What divides 18? No, the last one is 18, right?
I don't know. I was there with you.
You both said 12, so No, you're just in a different structure. You're not in the integers anymore. You're just in the rationals. 12 divides 18 just fine in the rationals.
I just started saying multiples with 3 and then kept moving.
Yeah. All right. And then again, we use the Euler phi function to count. So number of elements of order 1 will be 1. Good. Number of elements of order 2 is also 1. Elements of order 3 is 2. 6 is 2. 9. I know that one's a little harder, right? 9, 1, 2, 3 doesn't, 4, 5 doesn't, 6 doesn't, 7, 8 works. So there's 6 of them. It's also 9 minus 3. Because we have the, remember when you got the phi of p to the n is p to the n minus p to the n minus 1. 9 is 3 squared. So you do 3 squared minus 3. You do that one.
No, that is a
Your
easy
brain
to pull
works
off the
so
top of my head.
fast. I'm like, what the?
Remember, we talked about this property, right? Yeah. 9 is 3 squared. So we'll do 3 squared minus 3. That's where the 6 came from. This is basically there are p to the n integers from 1 to p to the n. Of those, there are p to the n minus 1 multiples of p. So subtract it out so you get the rest of relatively prime because you only have a prime divisor. That's how that formula works. All right. How?
So that doesn't work for if you were to say assume the number was p to the 1, that just falls through.
No, it doesn't.
6 minus 1.
6 is prime.
Oh.
Now, if you have a prime, if they're relatively prime, then you can break it up this way. Bring it up like that, and then you can do them in pieces. So you can prime factor your number first, and then multiply them together. And that's how I can do it that quickly. So for example, 18 is 2 times 9, or 2 times 3 squared. So I can do phi of 2 and do phi of 3 squared. 1 times 6 is still 6, and I don't have to count them. I can count them, but I don't have to, if I can factor it quickly. Again, this should add up to 18 when you're done, because we only did the rotations. Right? Does that add up to 18? I hope it does, because otherwise I'm an error somewhere along the way. I think it adds to 18. Okay. And then the other half of a dihedral group are the reflections. So how many elements of order? How many more elements of a certain order are we going to throw in there? We have 18 more elements of order 2, right? So in D18, we have for order 1, there's 1. For order 2, there are 19. What's the extra one, by the way? Think about this case. There's 4 reflections, but what's the other element of order 2?
180.
A 180 rotation. If you have an even number of sides, a 180 rotation works. If you have an odd number of sides, a 180 rotation doesn't work, right? So the number of elements of order 2 in a dihedral group will always be n if n is odd. It'll be n plus 1 if n is even. And you'll get the extra one for the 180 degree rotation. Order 3, there are 2. Order 4, there aren't any of order 4. Order 6, there's 2. Order 9, there's 6. And order 18, there's also 6. Okay. Shoo. So far, so good? All right. Are we okay with counting? Are we okay with counting elements in a cyclic group? Let's start there, because that's all I'm going to ask you to do, and then pair it with a another particular group. Are we okay with counting number of elements of a cyclic group?
That's the fee function.
That's the phi function, yeah.
And that's the numbers that are relatively flat.
Yep. Okay. Now let's look at the other group that they ask you about. But this time they only ask you about the elements of order 18 in D6 cross Z3. Ouch. That did not feel good. Just smack my back against the chalk tray. Don't do that.
I'll try not to.
Okay. What are you, or think about if you're doing a direct product and you need an element of order 18, I need to be able to create a least common multiple of 18. Or sorry, a least common multiple that gives you 18, right? That's how we got the order of elements in a direct product, right? Order of the first component, order of the second component, look at the least common multiple. Yeah? All right. Let's do the easy one first. What are the possible orders for elements in Z3? 1 and 3, right? Good. If I only have 1 and 3 to choose from, what's the order of the other piece going to have to be? Of the other component, if I'm going to get a least common multiple of 18. If I only have 1 and 3 to choose from for the second component, what would I have to use for the order in the first component to get a least common multiple to be 18? I'd have to use the 18, right? Yeah. I have to use the 18 to give me a least common multiple of 18, right? Because 3 divides it, right? Now I'm looking at D6. What are your possible orders of elements in D6? Well, again, D6 is made up of how many rotations and how many reflections? 6 and 6, 6 of each, right? All the reflections always have order 2. Can't be any reflections, right? Agreed? Your rotations form a cyclic group of order 6. What's the biggest order you can get from a cyclic group of order 6? 6, yeah, that's right. Yeah, because remember, cyclic means the order of the element has the same as the order of the group, right? So are there any elements of order 18 in D6? No, the biggest order is 6. So can I even get an element of order 18 in D6 cross Z3? No. So can D6 cross Z3 be isomorphic to D18? No, because they have different number of elements of order 18. Okay. Whew, let's recap before we go on to doing some stuff with symmetric groups today. Let's recap all this because this was a long example because we've already spent 55 minutes on it. Okay. Z36 was cyclic. Were any of the other groups cyclic? No. Can any of the so I know that Z36 is in a class all by itself, right? Can any of the first 3 groups be isomorphic to any of the second 2? No, because the first 3 are abelian, the second 2 are not, right? So we've got Z36 by itself to start with, and then 2 other classes that we had to deal with, right? Because we split up Z36 by itself was cyclic, 2 abelian groups, 2 non-abelian groups. So they can't be isomorphic to each other. Counted the number of elements of order, elements of different orders in the first 2 abelian groups. Those were different, so those can't be isomorphic. Did the same thing for the non-abelian groups, so those can't be isomorphic. So we actually have 5 non-isomorphic groups here of order 36.
Z36 abelian?
Yeah. Z36 is abelian. Every cyclic group is abelian because if I operate an element with itself over and over again, it doesn't matter what order they're all abelian. So we get 5 non-isomorphic groups of order 36. Turns out there's 9 more of them. There's 14 total.
I'm going to spend the next 20 minutes finding
No, you won't. Group classification is another one of those things that's hard. Especially the higher power primes you get that divide the order of the group, it gets difficult. If you have distinct prime factors, usually it's fairly straightforward. So for example, if you have 2 times the prime, there's only 2 groups of that order, period. One's abelian, one's not. It's either cyclic, Z mod 2p, or it's the dihedral group, dp, and that's it. That's all you get. But if you get something like order 64, there's like 255 different groups of order 64. Fun time finding them. Keeps you busy on a Saturday night.
Can I give me other things that I like to do on Saturday?
Really? You don't want to do group classification?
You could say that.
All right. Does it make a little bit more sense? A little bit more, hopefully. All right. Let's switch gears slightly to something we have talked about before, and that's our symmetric groups. This is section 7.5. I just want to talk about a couple of properties in here. We won't do a lot of things different than we've talked about, except we'll do one more definition. So, if I ask you to write this permutation and disjoint cycle notation. We've talked about doing this, right? So typically we start with 1, right? And then after that we map what the image of each particular element is. If we get back to where we started, we close off the cycle and go to the next symbol. Right? So where does 1 get mapped to? Okay, and 3 gets mapped to 2, 2 gets mapped to 1. So we close the cycle off. Right? That look familiar? Okay. Then start with a symbol that's not in the first cycle. 4 is not in there, right? Where does 4 get mapped to? 6 gets mapped to 4. So it closes, right? Pick the next symbol that's not in there. I'll use 5 because we haven't hit 5 yet. 5 gets mapped to 7. 7 gets mapped to 5, so it closes. The last symbol is 8. 8 maps to itself. I could write it, but I don't need to, because anytime that if a symbol's missing, we assume it's fixed. And writing a 1 cycle there would be fixed. So this would be changing the permutation into disjoint cycle notation, right? We like disjoint cycle notation for a few reasons. One, disjoint cycles commute with each other. It doesn't matter where you put them, even though this is function composition. Anything that's not fixed by this cycle is fixed by this one, and vice versa. So it really doesn't matter if I apply this function first and then this one, or this function first and then this one, because this just reorders the one. If you think about it as permutations, this only reorders the 1, 2, 3, and doesn't touch the 4 and 6. That reorders the 4 and 6, but doesn't touch the 1, 2, 3, right? So it doesn't matter if you mess around with the 1, 2, 3 and then mess around with the 4 and 6, or vice versa, you end up with the same answer. Okay. So disjoint cycles always commute, which allows us to get their orders a little bit faster. Because if they commute, then I can distribute the exponent over each component, each cycle. And then I can just compute the orders by doing the least common multiples of the orders of each cycle. So this element has order 6. This permutation has order 6. Because this has order 3. Because the order of a cycle is just the length of the cycle. This has order 2, this has order 2, and the least common multiple of 3, 2, and 2 is 6. So I know that the order of this particular thing is 6. This is why I would like disjoint cycles. We should be able to do that if I already have some cycles that are that are written out but aren't disjoint. So maybe I have 1, 7, 5, 2, 2, 3, 5, 1, 4, 6, 6, 7. Bless you. And I'm just making them up as I go along here. 3, 2, 7. I don't know. Just making things up. And just ask you to write this in disjoint cycle form. I'd start with 1, since that's the first symbol that appears. Remember, again, when we do these, we work from right to left, right? This is function composition. Where does 1 get mapped to? 4. Good. The only place 1, the first time I get to 1 here is here. This is 1 gets mapped to 4. I take 4, and it doesn't get moved by anything else. So 1 gets mapped to 4. Right? What does 4 get mapped to? 6. Because again, take 4 through here. The first place I see 4 is right here. 4 gets mapped to 6. I take 6 out and put it in the other 2, and it doesn't get moved. Does this look familiar from what we've done before? Where does 6 get moved to? 5, I agree. Start with 6 here. Doesn't move. Where does 6 get moved to here? 7. 7 doesn't move. 7 doesn't move. Here, 7 moves to 5, right? We agree? Now do 5. Where does 5 get moved to? Nowhere here. Nowhere here. Nowhere here. Here it gets moved to 2, and then 2 moves to 1. So this closes the cycle. What symbol do you think we should do next? 2? What does 2 get moved to? 7? I think overall it gets moved to 7, doesn't it? If I go all the way through.
Yeah.
2 goes to 7, which goes to 1, and then it goes to 7. So 2 goes to 7. 7 goes to 3, which goes to, if I'm just working my way over, to 5, which goes to 2. So this closes it again. What's not there? 3, and no, there's no symbol besides 3 that's left, right? So 3 better be fixed, correct? 3 better map to itself. We agree with that? Okay, does it? 3 goes to 2, 2 stays, 2 stays, 2 goes to 3, 3 stays. So 3 does get mapped to itself, so we don't need to write it. Remember, again, if a symbol doesn't appear, we assume it's fixed. Does this look familiar? We've done these before, haven't we? Okay. All right. So let's do one more concept that we haven't quite talked about yet, but it's not too bad. And again, I keep bumping things that open up. By a 2 cycle or a cycle that just has 2 elements in it, we call that a transposition. So we're just flip-flopping the positions. That's what we mean by transposition. If you've done any accounting at all at any point, or bookkeeping or what have you, a transposition means that you just flip-flop digits. It's a common error in accounting because if you're writing things down or typing things in, it's easy to flip-flop a digit. That's what a transposition is. So a lot of error correcting codes are designed to help find transpositions because it's one of the most common errors in data entry. For example, if you have a UPC barcode on your anything that you buy, ISBN in a book, those all have a check digit in it, which will catch transpositions and other errors too. But they will have the whole reason why you go through coding those things is because data entry, it's really easy to flip flop two things, super easy to flip flop two things, and those will catch them. Except, I don't think a UPC catches a transposition if the difference of the two digits is 5. Just because of the way it works. I think that's right. It's been a while since I've played with that, but I think that's right. As a theorem, every permutation can be written as a product of transpositions. It's distracting me. This is pretty straightforward, by the way. Without going through the whole proof, let me show you why it's straightforward. Let's just do a specific example, and then you can see how it extrapolates. I want to write a product of transpositions that equals this cycle. I'm going to use 1 as a bridge. I know it looks weird, right? I'm going to write 1 as a bridge. Okay. And then I need 1. Where does 1 need to get mapped to if I'm going to start it this way? If I want these two things to be equal, 1 better be mapped to 2, right? Well, I better not put the 2 here because 1's going to get mapped to something else over here, right? So I better put the 2 here. And then not put it in the other 2 because then 1 gets mapped to 2 and we're done, right? Where does 2 get mapped to? 3. Well, 2 right now gets mapped to 1. So where do you think I better map this 1? 3? And then can you guess what the other blank might be? 4, yeah. And you can do this for any cycle. I can always do this for any cycle no matter what. Okay? What's the length of the cycle here, by the way? How long is that cycle? The original cycle? How many things are in it? 4. So we call it a 4 cycle. Its length is 4. How many transpositions did we use? 3. Okay. So you can always do it with 1 less transposition than the length of the cycle. And then since I can write any permutation as a product of disjoint cycles, and I can do this for any cycle, I can write any permutation as a product of transpositions. Okay? So as another definition, a permutation is even if it can be written as a product of an even number of transpositions. So you can probably guess what the definition of odd is. The permutation will be odd if it can be written as an odd number of permutations. Or transpositions, sorry. So going up to the previous example, we had an even length cycle. That even length cycle is an odd transposition. An odd permutation, because it's written as an odd number of transpositions. Even length cycles are odd permutations. odd length cycles are even permutations. Because you can always write it as a product of one fewer transposition in the length of the cycle. Probably asking why we care. No. Good news is that we're not going to do a lot of why we care because it's a little bit harder than what I want to do, but I will talk a little bit about why we care. So I'm not going to prove the theorem because it takes a little bit longer than what I care about. Actually, this is more of a lemma than it is a theorem. The identity permutation, which means fixes everything, right? Identity permutation is the thing that moves no symbol. Is an even permutation. Since we're using the words even and odd, it's probably, well, I'll say obvious, but I don't mean obvious. It's probably clear that we can't be even and odd at the same time. I can't write a permutation as 13 transpositions and 26 transpositions because one's even and one's odd. Okay. The identity is an even permutation. A lot of times you'll see the Greek letter epsilon used to denote the identity. There's writing the identity as an even number of transpositions. I wrote it as 1, 2, 1, 2, right? Every transposition is its own inverse. Think about what a transposition is, right? It flip-flops where the two things are. Well, how do I undo a flip-flop where the two things are? Just flip them again, and they go back to where they started. Now, clearly, I could do other transpositions, right? I could do this, and I still get the identity, right? Or do this. But notice I have to add two of them every single time, right? I can't just add one. That's what would be the proof, is the fact that you try to add one and you show that you really had to add two to do it. So since the identity permutation is an even permutation, you can prove that to show that every permutation is either even or odd, but not both. There's a concept in topology that's called open, and there's a concept that's called closed, but it's possible for a set to be both open and closed, or so it's said to be neither open nor closed. So the fact that you use kind of an opposite thing is not a good idea for topology. If you're not offended by strong language, watch the video Hitler Learns Topology. Goes off a scene from a movie where Hitler starts yelling at his closest advisors, but it has topology stuff at the bottom. It's hilarious. At least I find it hilarious. Anyway, so let's go back up to the first couple of examples that we did. This cycle right here, is that even or odd? What's its length? Let's start there. 3. 3 is odd, so it's the cycle itself that is even, right? Because it's always one less. You can do it as one less than the number of transpositions, right? So since it has length 3, I could write it as 2 transpositions, so it must be even. And how many more transpositions did we stick on the end? Yeah, 2, an even number, right? So if I put an even number of transpositions with an even number of transpositions, how many do I end up with? Even number. So the whole thing itself will be even. Good. This one, that's going to be even or odd. Odd, and we added one more to it. So overall it's going to be even, right? Because odd plus, and it's the same idea that you do with numbers, right? Odd plus odd gives you even. Even plus odd is odd. Odd and even is even. works with permutations as well. So since it works with permutations as well, it's the last thing I'm going to mention today. We'll tidy this up on Thursday and do the last thing on Thursday that I want to do. The set of all even permutations of Sn we call this An, or the alternating group, is a subgroup of Sn. Turns out, and this kind of makes sense if you think about it, half of your permutations are even and half are odd. And the idea that if you combine an even and even, you get an even, gets you that the set of even permutations is going to be a subgroup. And it kind of makes sense, right? That there's half even and half odd. Because for every even permutation, stick a transposition on it, you get an odd. And for every odd, stick a transposition on it, you get an even. So there's a one-to-one correspondence between even and odd permutations. The alternating groups are the ones that would be more interesting if we had more time to study them. They have some interesting structures to them. Okay. So anyway, I will get a review posted today for, like I said, the quote-unquote in-class portion of the final. We've got one more concept to talk about, which I thought we'd get started today, but we just spent more time on the other stuff, which is okay. That happens. We're allowed to spend more time on other things. Basically, we just want to get to the point where we can understand that for any group, the order of a subgroup has to divide the order of the group. We've done that for cyclic groups, but we haven't done it for groups in general. That's what's referred to as Lagrange's theorem. It's a big theorem in group theory, so it's okay to end of the semester on that. All right. Have a good one. We'll see you Thursday.